Hello, everyone. Thank you for coming our conversation. My name is Zhang. I am from Washington State University. We are collaborating with Pacific Northwest National Laboratory, Boston University, University of Rochester. Today, I'm going to present our work, H-GCN graph convolutional network accelerator and Versal ACAP architecture. Then I will talk about a background of graph convolutional network. GCN are composed of stacked graph convolutional layers. Each GCN lays following aggregation and combination paradigm. In particular, the laywise for the propagation of GCN can be abstracted as this equation. So it is A dot X dot W. So A is self-looped adjacent matrix. D is Laplacian matrix. Particular, the widely used two-layer GCN model is as this equation. As introduced above, so the key computation pattern in GCNs is abstracted into matrix chain multiplication A dot X dot W. Next, I will introduce the background of Versal ACAP. So ACAP is fully software program and heterogeneous computer platform that combines three components process system, which is scalar engines that include ARM process, program logic, which is adoptable engine that include programmable logic block. Last one is artificial intelligent engines, which has leading edge memory and interfacing technologies. So the PL kernels can be C or C+ kernels or RTL kernels. Its program model is same as the traditional FPGA. Then I will talk about the AI engine. So Xilinx AI engine are array of very long instruction word processor with single instruction, multiple data vector processor. So an engine provides three levels parallelism. The first one is SIMD. So vector register allow multiple elements to be computed in parallel. Next one is instruction level. So VLSI architecture that allows multiple instructions to be executed in a single clock cycle. Last one is multi-core. So in engine array, there are up to 400 AI engines can be executed in parallel. So the AI engine array is C or C++ programs executed on those AI engine, which are writing using specialized intrinsic cores or AI engine API. Next, I will talk about the motivation. So as we observed that besides the irregularity, the heterogeneity of graph structure is also a significant reason limiting the performance. As shown in the figure, a graph can have tightly clustered components, loosely clustered components, and scatter nodes. So it is not possible to use a unified architecture or device to accelerate all paths of graph. For FPGA-based accelerator, its overall performance is significantly bounded due to the low frequency. So compared to the CPU and the GPU, however, CMD can provide a high frequency and computation power. However, its use scenario is limited because the fixed computation pattern. Next, I will talk about the proposed architecture. The figure shows the overview architecture of our proposed H-GCN. It consists of platform controller in processing system, sparse dense matrix multiplication unit, and the PL controller in Programmable Logic, and sparse dense systolic tensor array and activation explanation unit implemented in AI engines and network on chip for DDR SDRAM. So platform controller controls the whole system. The PL controller controls SPMM unit, and the sparse dense systolic tensor array accelerates both dense and the sparse matrix addition and multiplication. Then I will talk about the input graph reordering. The reason we do graph reordering is that real graph exhibit community structure. So some vertices may share neighbors or have close relations to each other. So it can improve data locality by modifying order of vertices. So we perform graph reordering at the pre-processing stage for only once. Then I will talk about the sparse tensor engine. So the essential matrix multiplication is multiply accumulate operation. So the matrix multiplication can further decompose into vector operation. So all AIE engine provides 512-bit SIMD vector unit, FPMAC and FPMUL. So FPMAC perform multiplication and accumulation for single precision, real number, real time floating point vector. And the FPMU does multiplication for single precision, real time, real floating point vector. So this is intrinsically designed and optimized for the dense matrix multiplication. We use row-wise SpMM and compress sparse row CS to increase the generality. So as shown in the figure is the illustration of SpMM. So then we'll talk about the limitation SpMM. So firstly, compiler cannot optimize SpMM. So since the number of innermost loops is not fixed, since the number of non-zeros in each row is not fixed. And second, the compiler cannot use pipeline or loop flatten to optimize such loops with variable number of loops. And the performance is worse than dense matrix multiplication with the same size. And besides, it has low memory bandwidth utilization, since CS formula leads to the random row data access. Then I'll talk about our proposed group SpMM. So basically, when we directly flatten out most loop, possibly solve the limitation, but direct expansion causes insufficient programming space area due to limited programming space. So we use moving average to divide the rows of matrix A into multiple groups, as shown in the figure. So the goals are each group contains as many rows as possible to save the programming space, and each row has at least little padding as possible to reduce unnecessary calculation on their rows. Then I will talk about the grouping algorithm. So for example, the line 8 to 9, we use the pre-average to record the previous moving average, and we use the CUR average to save the current moving average. So the line 13 to 18, if the change of moving average exceeded the threshold, we group the row J to row I-1 into a group, and padding each row in this group to ensure they have the same number of non-zeros element in each row. Then I will talk about the sparse systolic tensor array. So the two-dimensional systolic array is pipelined to the array of processing elements. So it has efficient local data movement, and then efficient execution. But for systolic tensor array, it has a tensor P, not a PE. The difficulty I perform SPM using systolic tensor array are, firstly, TPE in the same row are required to perform exactly the same calculation mode. But for SPM, each type has completely different number of the non-zeros element. So and the computational mode. So we propose automatically tensor P generation algorithm to enable SpMM on systolic tensor array. So for line 6 to 8, we count non-zeros of type in the same row. And for line 9 to 10, we calculate the average non-zeros and the maximum non-zeros of all times in the same row. For lines 12 to 14, we try to find a suitable number of non-zeros for all ties in the same row. If the difference between the average non-zero and the maximum non-zero is larger than the predefined ratio, and if we cannot find the suitable number, we select maximum non-zero as the ideal non-zero for all tie in the same row. So for the line 17, we use the grouping algorithm again to group the rows. So after generating the number of non-zeros in each row, and to obtain the final density of the padding. For the line 18 to 22, we directly use the dense tensor P for those ties if their final density is larger than D. Otherwise, we will use the sparse tensor P. Then I'll talk about the pipeline SPM chain. So SPM chains are executed on 3 different hardware. They are SPM chains are executed on 3 different hardware. For example, a dense systolic tensor array, sparse systolic tensor array, and P for SpMM. So there are 400. Well, P is distributed in 8 rows and 15 columns. So we used up 4 columns to do the mixed sparse or dense systolic tensor P to perform the computation of A dot B. So B is intermediate variables generated by the A dot W, and the remaining 4 lines are used for dense systolic tensor P to perform the computation of A dot W, X dot W. Then I will talk about the evaluation part. So I will first talk about the experimental setup. So we use 7 real-world dataset as shown in the table. We use 2-lay vanilla GCN model with the height dimension of 128. So for our platform, it is Versal VCK 5000 board with which features with the Versal ACAP XCVC 1902 device and 4 DDR. So our grouping algorithm CSR fixed non-zero. I provide 2.9, 2.1, 2.5 speed up on matrix on size of 64, 32, and then 16. And so, and the row-wise SPM with variable loop are much slower than the dense method. We also do comparison with state of art. So for inference latency, H-GCN outperforms I-GCN by 1.1, outperform both GCN by 1.5 to 2.3, and AWGCN by 1.2, and HYGCN 6.9 times. And for energy efficiency, H-GCN achieve 1.1, 1.6 more energy efficiency than I-GCN and AWGCN. So we also could do the comparison with CPU and GPU software. So as you can see that for H-GCN significantly outperform the PYG and DGL on both the CPU and the GPU. We also evaluated the overhead of graph reordering. So the graph reordering is integrated into the training process. So the OMP version of Mattis take advantage of multi-core in CPU. So so the table shows the overhead of graph reordering. Thank you.